interpolation of functions on Banach spaces and reiteration theorems. You have 25 minutes for your talk and 5 minutes for questions. You are welcome.
Thank you, Ivan. Thank you for the introduction. So, so, in this talk, we basically study the real interpolation. Classically, the real interpolation deals with the interpolation between a pair of Banach spaces. But in this work, we change this perspective that rather than interpolating between a pair of Banach spaces, actually we are interpolating between their respective norms, such that these norms are allowed to take values in closed interval 0 infinity, and the resulting interpolation function we have is again a norm, and the respective domain is just nothing, just the classical interpolation space between those two Banach spaces. We can find the examples of interpolation of some general functions like powers of norm in the book by Peter and Tartar, and in book by Berg and Lofstrom, and even more general functions in the work done by David Brazil and the Peters. These are some work done by them in 1980s. Before going ahead, I just want to brush up the classical real interpolation of a Banach spaces. If we are taking out a couple of interpolation couple of Banach spaces, say x naught and x1, then the real interpolation space, actually in the classical real interpolation theory, there are the various methods of characterizing the interpolation space. And one of the most prominent method is the K method. So here I'm defining the real interpolation space using the K method. So the real interpolation space is nothing just the set of all the elements x of the sum space x naught plus x1, such that the map t goes to k of xt upon t lies in this weighted LP space. That is the LP 0 infinity with the LP space on the R plus with the weight tp 1 minus theta minus 1 dt. Here theta is in open interval 0 1, and p lies varies from 1 to infinity. Here k is the k function associated to this Banach space defined like this. So this is just the K method to characterize the real interpolation space between a pair of Banach spaces. Now we will see the interpolation of functions. Throughout this talk, the function that we are taking are just the energy function, that is the function defined on a Banach space X, and they are taking values in the closed interval 0 infinity. And its effective domain is the set of all the elements of the Banach space X, so that at those points this function is finite, and we are denoting this effective domain by this symbol. So now we will see the interpolation, and by an interpolation couple of functions, I just mean a couple of measurable energy functions and not n1. Now we will see the Banach function space. Basically, a Banach function space is a Banach space of functions on R plus. This satisfies certain properties. The first property is that it lies in between L1 intersection L infinity to L1 plus L infinity. And the second property is that E is an order ideal of L1 plus infinity. That is, if if f we are taking any two functions f and g on L1 plus L infinity, such that the mod of g is less than equals to the mod of f, and the right hand side f is in E, then this implies that the function g is also in E, and the E norm of g is less than equals to the E norm of f. One of the typical example of a Banach function space is the weighted LP space, basically polynomially weighted LP space. If we closely look at this space is the same one that we are talking in the previous slide for the classical real interpolation theory. So in the classical real interpolation theory, the only Banach function space that we are using is only the polynomially weighted space. But our work is holds for all the Banach function spaces. Now we will see the K method. As I already discussed, the K method is one of the most prominent method used in the classical real interpolation theory to characterize the real interpolation space. And even for our work, this is equally important. So if we take any interpolation of couple of functions, that is just a pair of two measurable energy functions. And we are taking EB and Banach function space over R plus, then we define a K function corresponding to this interpolation couple at at any point x of the Banach space x is the defined as inf of n naught x minus v plus t of n1 v, where v varies over all the members of the Banach space x. So corresponding to this interpolation couple of functions and using this K function, we define an interpolation function for any tau positive. We define an interpolation function denoted by this symbol. It is basically an energy function on the Banach space x defined by that the value of that interpolation function at member x of the Banach space x is just the E norm of this K function, with the interpretation that if that function does not lie in the Banach space E, then the value of this interpolation function at that point x is just infinite. And we define the interpolation set is just the effective domain of this interpolation function. Now we will see how the classical real interpolation theory, basically which is a linear interpolation theory, fits it into our setting. So we are taking our interpolation couple x0 x1 of Banach spaces. So that is then this sum that we are calling the sum of these two spaces, say x, it is again a Banach space with this norm. So for fitting this theory in for our result, we need to define n naught and n1s. So we are defining our n naught and n1 our measurable energy functions like this, that the value of the function at a member x of the Banach of the sum space x naught plus xi is equals to the xi norm of that element x if that element lies in the Banach space xi, and infinity if that element does not lie in that Banach space xi. These two energy functions satisfies all the properties of the norms, except that they are allowed to take values in the closed interval 0 infinity. That is, infinity is also included. So when we interpolate, so when the interpolation function that we get after interpolating between these two functions, then the effective domain of that function, that is just the equals to the classical linear interpolation space between the pair of Banach spaces. So in this way, we can say that interpolating between Banach spaces x0 and x1 is equivalent to saying that we are interpolating between their norms on the sum space x0 x1, with the smaller difference that our norms are allowed to take values in the closed interval 0 infinity. Here we have some more examples. If we have a couple x0 x1 of Banach spaces, now we can define some general functions that is just the power of norms. We can see such examples in already existing literature, that is in the book by Peter and the book by Tata, and they are calling it as a nonlinear interpolation. Now we will look at the M-accretive operator. Our relation A, here X is a Banach space. We are calling any relation on the Banach space X as an operator. Our relation A from X into X is said to be an accretive operator of some type omega if for every a pair of two ordered pairs in A and lambda positive, such that lambda omega is less than 1, the norm of x minus x hat into 1 minus lambda omega is less than equals to the x minus x hat lambda f minus f hat. So basically, if we want to imagine that operator in the on the real line or the on the R square. It is just a graph of a it's just a monotone graph or a non-decreasing, or basically we can say the non-decreasing graph. If we want to imagine an accretive operator on R square, so uh, if we take any operator A, if this operator is an accretive operator of some type, then we have for every lambda positive such that lambda omega is less than 1, this operator I plus lambda I is injective. Also, we say an operator A is an unaccretive operator of some type omega if it is accretive of type omega, and also the I plus lambda I for all those lambda positives such that lambda omega is less than 1 is surjective onto X. So in this way, we say if A is an unaccretive operator of some type, then for all of time omega, then or for all those lambda positives such that lambda omega is less than 1, these I plus lambda I are bijective maps. So we denote J lambda is equals to I plus lambda A inverse for the resolvent of A. So if A is amaccretive operator, then this resolvent of A is defined on the whole of X, and it's a single valued function. And also with using this definition of amaccretivity, we can also see that this resolvent is an Lipschitz function with Lipschitz constant 1 upon 1 minus lambda omega. So in the further slides, we apply our interpolation of general functions to amaccretive operators, and the interpolation couple that we are considering for the next slides are the couple in which the first function is just the norm on X, and the second function is the set norm A. Basically, as our operator A that we are taking is just a relation, so the set norm A at any member X of the domain of A is is defined as infimum of all those X norm of Y such that Y contains in AX. Now we have the Crandall-Liggett theorem. Crandall-Liggett in Evans theorem is basically just a nonlinear version of Luhmann-Phillips theorem, which shows the existence of the nonlinear semi. Let A be an amaccretive operator on a Banach space X of subtype omega, and then for every X in domain of the closure, the homogeneous abstract Cauchy problem with the right hand side 0 admits a unique solution. And if we set our solution ut as a, basically, I'm sorry for the mistake. Instead of this u0, it's x. I'm sorry for this mistake. So if we set our the solution is this st of ut of x, then this s is a strongly continuous contraction semigroup on domain of a closure of some time omega. This Crandall-Liggett even Evans theorem is, again I'm repeating, is just a non-linear version of Luhmann-Phillips theorem. Now we will apply to the general interpolation of functions to the interpolation couple associated to an amaccretive operator A. So here we have a result. In this result, we characterize the interpolation sets corresponding to the interpolation couple associated to an amaccretive operator A. So in the first characterization, we are using the resolvent operator corresponding to that operator A. In the second one, we are using the semigroup. And in the third characterization, we are using the K function, which is the standard definition that we are taking. And in the fourth characterization, we are using the derivative of the variation function of the resolvent. So the statement of this result is as if we are taking A to be the any amaccretive operator on a Banach space X and S be the semigroup generated by the minus A. This such kind of semigroup exists by the Crandall-Liggett theorem. And if we are taking an interpolation couple associated associated with the operator A, where the first function is the X norm, the second function is the set norm of A, and E be any Banach function space. And we are taking one more condition on the Banach function space that the Hardy operator is bounded on E. Then for every tau positive, we have all these four characterizations of the interpolation sets. Now, it is also well known that if the initial value of the homogeneous abstract Cauchy problem lies in the domain of A, then the solution of the that homogeneous Cauchy problem is a Lipschitz continuous function. And also, if that initial value lies in the domain of a closure, then the solution of the homogeneous Cauchy problem is actually a continuous function. So the question that is coming are in mind when we are studying for the interpolation, what will happen if we take the initial value in between domain of A or a domain of a closure, that is the interpolation set between the domain of A or a domain of a closure. So sorry. So basically, the result that we have now, that if we take the initial value in between the domain of A and domain of a closure, that is just the effective domain of the interpolation function associated with the interpolation couple. Oh, sorry, interpolation function of the interpolation couple associated to the Amakrativ operator A. Then the solution of that abstract Cauchy problem is in the interpolation set between the continuous space of all the continuous functions and the space of all the Lipschitz continuous functions. So, so as I already said, our solution satisfies some same kind of property that is in between the Lipschitz continuity and the continuous function. So when we closely work on it, then we have that the solution of that homogeneous Cauchy problem satisfies an Holder type estimate, which is the statement of that result is as if we are taking A to be an any Amakrativ operator and S be the semigroup generated by minus of A, and any be the any interpolation couple associated with A, and we are taking E as a Banach function space such that the Hardy operator is bounded on E, then for if our initial value x lies in the interpolation set, then for every t positive and time t in that enclosed into 0t, we have this estimate, which is certain, which looks like a Holder's type estimate. Also, we have one more result, that is the perturbation result. So in this result, what we are doing, we already have a Amakrativ operator A. We are perturbing operator A to and by the operator B, where B is dominated by A, uh, such that B is dominated by A and A plus B is Amakrativ operator. So the result we have that if the interpolation set of the interpolation couple associated with the operator A contains in the interpolation set associated to the interpolation couple interpolation set of the interpolation couple associated to the operator A plus B. And if we take our operator B to be a single valued function, then these two interpolation sets coincides, that their effective domains are equal. So now, as reiteration theorem already exists for the classical data interpolation theory, so when we are working on reiteration theorem for our setting, so we have certain conditions and certain reiteration theorems also. So first I define the k row condition. What is exactly a k row condition that we are calling? So let n naught n one n one hat are some energy functions. That is, these are the functions on a Banach space X that are taking values in the closed interval 0 infinity, and rho be any continuous function such that its inverse exists. Then we say a function n1 satisfies the k row condition with respect to the couple n naught n1 hat. The k function associated to this couple is less than equals to rho inverse t n1x for every time t positive and x in the Banach space element x of the Banach space x. So using this k row condition, we have certain iteration theorems. So the first iteration theorem we have, in this iteration theorem, the first couple that we are taking are a couple of functions n naught n1. These two functions are satisfying one more property, that these are subadditive functions of Banach space X. And the second couple we are taking n naught n1 hat. Here the first function of both these couple are same, and the second function are different. And but all these functions satisfying the subadditivity property. And suppose that the function n1 hat satisfies the k-row condition with respect to the first couple, and the function n1 satisfying the k-row inverse condition with respect to the couple n hat, that is the second couple. And we are taking a pair of Banach spaces E and he hat that satisfies certain kind of relation. There is some kind of relation between the pairs of these two Banach spaces. That is, for every a b, for every function f in E, there exists some constant a b positive, so that this relation holds. That is, a of E norm of t goes to ft upon t is less than equals to the E hat norm of t goes to f of rho t upon t is less than equals to b of E norm of t goes to ft upon t. So when all such assumptions or conditions are satisfied, then we have the interpolation function associated to the first interpolation couple with Banach function space E is equivalent to the interpolation function corresponding to the second couple with Banach's function space E hat. That means basically that their effective domains are equal. So if we interpolate in between the these two couples with different Banach spaces that satisfy some kind of property, then we have their interpolation set or their interpolation sets are equal. Now we have one more reiteration theorem, that again we are taking the same couples, that first couple to be the n1 n1 and not n1, the second couple to be the n not n1 hand. These all again these four functions subadditive functions where the first function is same. But now we are taking two rows rather than taking one row. We are taking two rows, and now here some condition is changed, like the here n1 satisfying the k row not inverse condition. We are taking two rows. First one is row naught and second one is row one. So here n1 satisfying the k row not one inverse condition with respect to the second couple, and n1 hat satisfying the k row one inverse condition with respect to the first couple. So again we are taking a pair of Banach spaces E and he hat which satisfy some kind of relation between their members, that for every f in E, there are just some constants C and D, such that D, the E norm of t goes to f of rho 1 t upon t, and its exception to the 0 tau is less than equals to the E1 norm of the function t goes to ft upon tau, and its exception to the 0 tau is less than equals to C, the E norm of t goes to f of rho naught inverse t upon t, and its exception to 0 tau. So basically, that by if all such conditions are satisfied, then we have the interpolation couple associated to the interpolation function associated to the first interpolation couple with Banach function space E is equivalent to the interpolation function associated to the second interpolation couple with Banach function space E hat. That is, their effective domains are equal. So using these two, the classical linear interpolation theorem fits into this second form, where we are taking rho naught and rho one, that suitable rho naught and rho one, like t theta I or t 1 upon theta naught or t 1 upon theta 1. So these theorems are also generalizing the classical iteration theorems. So here are the references that we are using. The first book for the good stuff of real, already this is real interpolation spaces. Second book contains some example of nonlinear interpolation of some general functions like the powers of norm. And in the fourth one, the thesis by the David Brazes and the Duffetels, we can find some general examples of interpolation between functions. And then the last is the work done by me and my supervisors, and it is on archive. Thank you, everyone. Any questions?
Thank you for the very nice talk. Questions, please. We have time for questions.
May I pose a question?
Please.
Thank you.
Yes.
Okay, very interesting. It was, maybe it's completely unrelated, but during your talk, I was thinking people are trying already for a long time to somehow to make a meaning of a sum of two generators. So you have basically two semigroups, and then the idea is, and they do it sometimes in numerics, and that they simulate the trajectory by first going over one semigroup for a short while, then switch to the other semigroup, and then switch back again. And that should somehow be then the semigroup hand generated by A plus B. Now that's only, or A1 plus A2. That's only true if A1 and A2 commute, so it's hardly ever the case. And I was wondering if this interpolating idea could help with this problem. That was just a thought that came up with me, because you are also intertwining somehow spaces, but I would like to intertwine semigroups. Yeah, you see what I mean?
Yes. So basically, you are talking about the interpolating between the semigroups or their generators, basically.
Yeah.
Yes, we are thinking on this direction, and me and my professor Ralph is also working on it, and we also, after this, maybe we are thinking about it, but not, we don't have anything concrete till yet.
No.
But yes, thank you. It's a really good suggestion. Yes.
Okay. Success with this, yeah?
Yes.
More questions? Well, then I have a question. From your point of view, what is the main result in your talk? The intriguing thing which you consider the main?
I think the solution part, when basically this result, I really found it interesting, and even I have a much more general result than this, uh, but actually it is already existing in the literature that if initial value is lies in the domain of A, and the right hand side f of the abstract Cauchy problem is just a BV in the BV space, and the solution is a Lipschitz continuous, and in the reverse, if the initial value is in the domain of a closure and the right hand side in the L1 space, then the solution is continuous. So this is a kind of a question that what will happen if those initial values and those right hand side f lies in those interpolation spaces. So is this solution also lies in the interpolation space or not? The answer is yes, it is. So this is kind of a result that is I find good, and I'm thinking about the application. But yes, we found some applications to Laplacian operators. So this result I really found good.
Thank you. Congratulations.
Yes.